During this presentation, we will demonstrate proper cockpit procedures to include interior check before starting, engine start and run-up, before takeoff, and engine shutdown. Following these procedures step by step will assure you a safe flight. Let's assume all exterior checks have been made. As we continue with the interior checks, take a good look around the cockpit to ensure all loose equipment is secured. Ensure that the pilot door is secure. Check to ensure that the emergency release handles are secure. Adjust pedals for personal comfort. Securely fasten seat belt and shoulder harness. Check shoulder harness lock for proper operation and leave unlocked. Now check freedom of movement of flight controls by pushing the tail rotor pedals back and forth, checking for any binding in pedal movement. Release both cyclic and collective friction. Move cyclic stick in a circular motion, checking for any binding of cyclic controls. Note, if co-pilot cyclic stick is in stowed position, assure electrical plug is connected. Move collective up and down, checking for freedom of movement. Leave collective in down position and set friction as desired. Caution, if battery and fuel boost pump switches are on and throttle is open before motoring engine, fuel will flow into the combustion chamber and can contribute to a turbine outlet over temperature start. Check the throttle for proper operation by rotating the throttle to the full increased position, then roll back to idle stop. Press idle release button and roll throttle to the full off position. Make sure the landing light switch is in the off position. Check all radios off and set to the desired frequency. Check engine instruments for static indications and operating range limit markings. Radio bearing heading indicator must be checked for security and current calibration card. Check turn and slip indicator for security, ball in race, and race full of fluid. Now place the directional gyro magnetic switch to the magnetic position. Ensure that the IFF code switch is in the off position. Place force trim switch to the on position. Hydraulic boost switch to the on position. Check vertical speed indicator for security and note static indication. Set altimeter for proper field elevation. Next, cage the attitude indicator and lock it if lock is installed by rotating the knob clockwise. Check the airspeed indicator for static indication, slippage mark, and operating range limit markings. Check the clock for proper setting and ensure it is running. Check magnetic compass for fluid level, heading, and current deviation card. Check the free air temperature gauge for security and note reading. Above your head and on the right of the overhead console is the fuel valve handle. Check security and condition of the mounting bracket. Check for proper operation by placing the handle to the off position, aft, then back to the on position, forward, and leave in the on position. On the overhead console, place the following switches in the prescribed position. Inverter switch off. Non-essential bus switch normal. Manual for night. Generator switch off. Battery switch off. Auxiliary receptacle switch off. Engine de-ice switch off. Pitot heater switch off. Defog and vent switch off. Heater switch off. Engine oil bypass switch off. Note: in a combat situation with the possibility of oil cooler failure, oil cooler bypass switch should be in the auto position. Place position light switch to the off position and the anti-collision light switch off. Rotate console and instrument lights rheostats counterclockwise to the off position. Check all circuit breakers in. Now, make sure the map light is off. Put your helmet and gloves on. Now turn the battery switch on. If this were a night flight, position lights would now be turned on. Check illumination of the warning panel by pushing the Press to Test button. Note: if the engine out warning light is not illuminated, check circuit breaker in. Do not fly the aircraft until the malfunction is corrected. On the lower console, test the caution lights to ensure they are operative, to include the master caution. Reset master caution switch. The caution lights will go steady bright and the master caution light will be extinguished. Place engine relight switch in the off reset position, down, then place to the relight position, up. Note: two types of switches may be used. One is spring-loaded to the relight position. The other does not utilize the spring-loaded position and must be manually pressed to the relight position. Raise the collective and listen for the engine out audio in your headset. Decrease the governor RPM switch for 7 seconds. Recheck the throttle in the full closed position. Now we are ready for engine start and run-up. Let us review some precautionary measures, limitations, and procedures prior to starting. Also keep in mind the maximum wind limitations for starting and stopping the OH-58A Kiowa is 45 knots. Caution. In case of false start, or a start not completed in a total time of 45 seconds, close throttle and motor engine with throttle closed for at least 10 seconds and until residual TOT indication reads less than 200 degrees centigrade. At outside air temperature of 10 degrees centigrade or below, allowable total starting time is increased to 60 seconds. If starter relay chatters during start cycle, it is an indication of low battery power. Abort start and use APU or recharge battery. During the start cycle, the engine relight bulb may illuminate. When APU is used, the bulb may illuminate immediately after the starter switch is depressed. When battery or low output APU is used, the bulb may not illuminate until actual engine light off. The throttle will be open to idle at peak of N1 RPM provided the TOT is not above 200 degrees centigrade and the following N1 RPM limits are maintained. 15% and above at 7 degrees centigrade through 54 degrees centigrade, 13% and above at minus 18 degrees centigrade through 7 degrees centigrade, 12% and above at minus 54 degrees centigrade through minus 18 degrees centigrade. If the main rotor is not moving by 30% gas producer speed, N1, abort start and investigate for possible mechanical failure or drive system malfunction. The TOT indicator should be monitored for any over-temperature indication. During the start period, anytime 749 degrees centigrade is exceeded for more than 10 seconds, perform engine shutdown and record peak temperature and duration. Maintenance action is required before next flight. Anytime 927 degrees centigrade is exceeded, perform engine shutdown and record peak temperature and duration. Maintenance action is required before next flight. The starter button should be released anytime between 58 and 62% N1. We have reviewed some precautionary measures, limitations, and procedures. Now we will begin engine start and run-up. Check rotor blades clear and untied and fire guard posted.
Clear! Clear!
Depress and hold starter button. Monitor the N1 gas producer gauge. When N1 reaches correct percent, roll throttle to the left until idle stop button pops up. Monitor N1 and TOT gauges. Ensure rotor blades are turning by 30% N1. Monitor the TOT and engine oil pressure. When N1 reaches 58 to 62%, release the starter button. Check engine oil pressure for normal indication. Transmission oil pressure warning lights should not be illuminated. Check engine idle between 62 and 63% N1. Place engine relight switch to the off reset position, down, then to relight position, up. Engine relight bulb should not illuminate. Place generator switch to the generator position. Check DC amp meter for normal indication. Caution, do not turn on radios or inverter until generator output decreases to 50 to 60 amps. Place inverter switch to the inverter position. Turn all radios on. We must now check force trim for proper response. Switch off the force trim and check the tip path plane. Caution, limit cyclic movement to 2-inch maximum displacement. The rotor is responding properly. Check flight controls for freedom of movement. Now for the hydraulics off check. Warning, before any movement of controls with the hydraulic system off, both hands must be on the controls. Place hydraulic boost switch in the off position. This will cause the master caution light and the hydraulic pressure caution light to illuminate. Reset the master caution light and continue the hydraulics off check. Check freedom of cyclic control movement by moving cyclic 45 degrees left forward, back to neutral, then 45 degrees right forward, then back to neutral. Now check freedom of collective control movement by increasing and decreasing collective pitch. Place the hydraulic boost switch back to the on position. Note, feedback forces will be encountered when moving the cyclic stick. If hydraulic servos are functioning properly, negligible force will be required to maintain a given stick position once stick is stopped by the pilot. Turn the force trim switch on. Slowly increase the throttle to full increase. This will give you 97% in 2. Increase the N2 governor switch on your collective control head through full range. This brings the N2 up to 104%. Now decrease the governor to bring the N2 down to 103%. This is your normal operating RPM. Now place engine DI switch to the on position. Check for rise in TOT. Place engine DI switch to the on or off position as required. Note, when anti-ice is on, TOT will be higher for the same power setting as with anti-ice off. Place pitot heater switch on. Check for indication on the DC amp meter. Place pitot heater switch to the on or off position as required. Place the defog and vent switch to the on position. Check for indication on the DC amp meter. Then turn the defog and vent switch off. Turn the heater switch on and rotate heater rheostat. Check for rise in TOT. Turn the heater switch off. Turn the interior lights on or off as required. Unlock the attitude indicator if lock is installed. Now check your flight instruments. Turn on the anti-collision light switch. Collective friction and force trim as desired. This concludes the interior check before starting, engine start, and run-up procedures. We are ready for a before takeoff check. The before takeoff check includes no warning lights, Engine instruments in normal operating range. Fuel quantity checked. Engine RPM 103% in 2. Engine relight switch to engine relight position if installed. Caution lights off. And fuel boost pump switch off for takeoff below 10,000 feet MSL. The final check to be performed is the engine shutdown procedures. Roll throttle to idle stop and allow to idle for 2 minutes. Turn the force trim on. Now center the cyclic, push collective full down, and set friction on the cyclic and collective. Place the anti-collision light switch off. Turn all radios off. Then turn all electrical switches off except generator and battery. Note, if the amp meter indicates a charging rate greater than 10 amperes at idle with all electrical load off, continue operating the engine until the amp meter decreases to the range of 5 to 10 amperes, thus indicating that the battery is approaching a fully charged state. Fully close the throttle and monitor the TOT. Note, with engine relight switch in the relight position, the bulb will illuminate when the throttle is closed. This indicates the auto relight system is operable. Position lights as required. Now turn the generator switch off. Caution, before turning battery switch off, ensure TOT is stabilized below 400 degrees centigrade. If TOT rises above 400 degrees centigrade, this indicates a residual fire in the engine. Motor engine with throttle closed for at least 10 seconds, and TOT indication reads less than 200 degrees centigrade. Now turn the battery switch off, and if aircraft is armed, pull armament circuit breakers. Tie down the main rotor blades.
Following a post-flight inspection, complete DA Forms 2408-12 and -13.
This completes the demonstration of the cockpit procedures on the OH-58A Kiowa. Following your checklist step by step will ensure aircraft dependability and your safety during the flight.
Damned if I know what happened. I pulled in collective to get light on the skids and it rolled right over. Happened so fast.
We get the word to go, so I go, right now. Pull pitch and over it goes, right roll. Blade pieces flying all over the place, transmission way out there somewhere, all over in a few seconds.
Level ground, no crosswind, piece of cake. How could it happen so fast? I can't count the takeoffs I've made. But this time, wham, roll right, and we're climbing out the left window. What happened?
Dynamic rollover. That's what happened. What we aim to do is help you understand how dynamic rollover accidents happen, why, and what you can do first to prevent it from happening, and then how to correct for rollover if you think you're getting into trouble. At the United States Army Safety Center, we're concerned about the frequency of dynamic rollover accidents. Here's why. In a 10-year period studied, there were 25 dynamic rollover accidents. 8 of them in a 13-month period, and of these, 7 were to the right on level ground. As a matter of fact, 21 of the 25 have been right rolls. Dynamic rollover happens on level, prepared, and unprepared surfaces. Nobody is immune. Not the student pilot, not the IP who's teaching him, not the pilot with 150 hours, not the pilot with 2,000 hours, not you, whatever your training or experience has been. The reason is, dynamic rollover seems to relate to your concentration on the job at hand, your degree of attention at the critical moment of liftoff, and how you handle the controls. It's a procedural problem, not an equipment design or malfunction problem. And it all goes back to the first thing you learned in basic flight training, how you get that helicopter off the ground. Because if you always follow correct procedures in accordance with the aircrew training manual, you'll never have a dynamic rollover accident. That's why in the next few minutes, we'll go back over the right way to perform liftoff to hover. With the correct procedure firmly in mind, we'll show you what can happen to induce dynamic rollover in 4 basic situations. Rollovers to the right and left from level ground, and rollovers on liftoff from both right and left slopes, and show avoidance and recovery procedures. We'll touch on the various helicopter types to see what effect their flight characteristics might have on the problem of rollover. And we'll look at various prepared and unprepared surfaces and their possible contributions to rollover. Finally, we'll go back over correct liftoff procedures one more time. Although all single rotor helicopters are subject to rollover, we'll be looking at the UH-1 for convenience. We'll look at the situation along the longitudinal axis from the tail of the aircraft to keep the directions in which forces act on it clear and simple. Sensing the effects of those forces is part and parcel of correct liftoff procedure. With before takeoff check completed and aircraft clear, you verify that cyclic and pedals are in neutral position. Slowly, you increase collective with a smooth, constant, positive pressure to get the aircraft light on the skids, with main rotor thrust equaling aircraft weight, so you can check control responses during this time. You apply pedal to maintain constant heading, applying cyclic as necessary to prevent sliding as the aircraft gets light on the skids. You maintain smooth application of collective with cyclic coordination to prevent drift, while maintaining vertical ascent and heading until you reach hover altitude. Smooth, well-coordinated control handling, making the aircraft do what you want it to do, with absolute concentration on the task at hand during those few critical moments before and as liftoff occurs. That's what it takes, this time and every time you take off. The penalty for failing to do so could be dynamic rollover. You could be penalized for being in a rush, failing to pay attention, and for rough handling of the controls, especially the collective. To show you how quickly dynamic rollover can happen, let's watch it in animation. In a moment, we'll let the animation go through right rollover in real time. Watch closely, because it won't take long. Okay? Go. One more time. Go. Main rotor blade pieces scatter. Transmission departs the airframe, structures are damaged, and pilots are lucky to avoid serious injury when dynamic rollover takes place. As you could plainly see, rollover happens so fast you're likely to be completely surprised by it, as some rollover victims have put it. One pilot said there didn't seem to be a thing he could do about it, as the aircraft rolled to the right. What you can do about it, of course, is never let dynamic rollover get started in the first place. And you do that by following correct takeoff procedures every time. But dynamic rollovers have continued to happen. And to give you a better feeling for how and why they happen, let's slow the action down. Break the problem down into smaller pieces so we can get a grip on it. Then we'll talk about the hows and whys of rollover avoidance and recovery. With the aircraft level and controls in neutral, let's review the forces acting on the helicopter before liftoff. The force, due to gravity, always acts toward the center of the Earth, as represented by this arrow from the center of gravity. Two more arrows show the reaction forces acting upward to counter the weight of the aircraft at each skid. The thrust force of the main rotor always acts at right angles to the tip path plane. If thrust is less than the force due to weight, the aircraft remains on the ground. Increasing collective increases thrust force. When this force equals aircraft weight, the helicopter is light on the skids, ready for liftoff. The main rotor rotates counterclockwise, and a reaction force due to this torque wants to turn the nose clockwise. But applying left pedal generates tail rotor thrust in the opposite direction and is used to maintain heading. Tail rotor thrust can cause the aircraft to drift right, so left cyclic is used to change the direction of the main rotor thrust to the left by the amount needed to cancel out the drift force. When these opposing forces are equal, the aircraft remains laterally over the same point on the ground. With all forces acting on the aircraft similarly coordinated and balanced, as collective is increased, main rotor thrust exceeds weight and the aircraft lifts off, right skid first in the UH-1, slightly nose high, so that the left skid heel is the last to lose contact as the aircraft rises. This sequence varies in other aircraft with different takeoff attitudes. All right, that's the situation in a normal takeoff executed according to correct procedure. But we're saying that dynamic rollover can happen mostly to the right and also to the left while the aircraft is sitting on a level surface. And we're saying that pilot procedure and behavior is the problem. That's with no complicating factors of crosswinds, lateral CG offsets, or slope, although all these can aggravate the problem. How come? Well, let's dig a little deeper and look at what happens when you handle the controls roughly or abruptly. Let's pick it up at the point where the aircraft is light on the skids. You've got some left lateral cyclic in, and left pedal is counteracting main rotor torque. Left lateral cyclic has done one more thing we didn't mention earlier to keep things simple, but now we've got to add it in. The direction of main rotor thrust has shifted to the right of the center of gravity, shown by this dashed line. When the aircraft is airborne, and with some left cyclic applied, its center of gravity always wants to align itself with the direction of main rotor thrust to get the aircraft back into trim. This sets up a roll moment around the CG toward the left, partly offset by right roll due to the weight of the aircraft. The result is that in hover, for example, the aircraft tends to position itself in slight left roll, or left side down. With the aircraft on the ground, none of this can happen. When left cyclic is applied, skid friction with the ground or an obstacle sets up horizontal reaction forces that prevent the skids from moving left or right. The aircraft still wants to roll left due to left cyclic, and the CG still wants to align with that thrust direction. That is, move the fuselage toward the right, but it can't because of the skid friction. This impulse toward the right generates a rightward roll moment, not around the center of gravity, but around the right skid. And it is this event that sets up the conditions for right rollover if controls are improperly applied. The distance through which this roll moment is acting, or its moment arm, can be shown by this bracket. The weight of the aircraft sets up its own leftward roll moment around the skid, and the distance through which it is acting, or moment arm, is shown by the lower bracket. This is longer than the right roll moment arm, so left roll moment, due to weight, acts as a stabilizing force, resisting right roll at this point in time. The result is nothing's happening, but the situation is about to change abruptly. To keep things simple, let's assume you leave left lateral cyclic where it is throughout the following and ignore the effects of yaw, though of course it would add to your problems. Now let's say you abruptly increase collective to get off the ground fast and rapidly apply left pedal. Two things immediately happen. Main rotor thrust increases, overcoming aircraft weight, and tail rotor thrust to the right goes up, well above the leftward force due to left lateral cyclic, which remains the same as it was. This means we've got a net force to the right, and so the power of the roll moment around the right skid increases dramatically, boosted by that large increase in thrust. That's big enough to overcome left lateral force and aircraft weight, big enough to start rolling the aircraft to the right at a high rate. We'll hold at 2 degrees so you can see what happened. For one thing, the reaction force under the left skid is gone, so the weight of the aircraft is pivoting around the right skid alone. This has moved CG over the ground rightward, toward the skid, beginning to shorten its moment arm, and so reducing its stabilizing ability. Further, you've set all that weight in motion to the right, and its momentum is going to keep it going that way until some force acts to stop it, and it will keep accelerating as long as collective keeps increasing. If you haven't recognized what's going on and started recovery procedures, considering we're only a second or less past applying collective, hard to believe as it may seem, you may already have lost control of the situation under certain critical conditions we'll talk about later. Now, let's unfreeze the action and see what happens. Let's hold again at 5 degrees. Main rotor thrust force has grown, and this adds a little to leftward force due to left lateral cyclic, which should be a stabilizing force. But rightward force due to tail rotor thrust has grown even more with left pedal application, overcoming left lateral force. The right roll moment becomes more powerful as collective increases. Meantime, CG position over the ground has continued to shift rightward, reducing the stabilizing capability of this moment arm. Once again, let's unfreeze the action. We'll hold at 8 degrees to point out that recovery action depends on using left cyclic and reducing collective to counteract right roll. But you've already used a few degrees of left cyclic, leaving a smaller margin of control available if you're going to avoid mast bumping. Furthermore, any corrective action has to have been completed from 5 to 8 degrees into the rollover for any chance of success, because it will take time to counteract the momentum of all that weight, and the aircraft is still accelerating rightward. In this case, no recovery action is taken, so let's continue. By about 15 degrees, only a couple of seconds, you're at the point of no return, the critical angle beyond which no recovery is possible, due in part because even full left cyclic can't reverse the situation. This would generate a large leftward force, but even with left pedal neutral, eliminating rightward thrust from this source, a right roll moment still exists. Decreasing collective will reduce its force, but because main rotor thrust is right of vertical, recovery is impossible and right rollover must continue. Eventually, rightward motion of the CG has brought it over the right skid. The stabilizing ability of aircraft weight acting leftward around the skid has disappeared because its moment arm has diminished to 0, while the right roll moment continues to act strongly along its moment arm. Once CG gets beyond the balance point, there's no saving it. Aircraft weight, now to the right of the skid, adds its force to the right roll moment, and rollover is inevitable. If your attention and concentration are elsewhere, and you're not handling your controls smoothly, you could wind up in a situation like this, wondering what in the world happened. Avoiding dynamic rollover requires close attention and concentration in the early seconds of the takeoff maneuver. If you're smoothly coordinating your controls, responding sensitively to the forces acting on your aircraft, the way you were taught from day one, you're not going to get into trouble. But suppose right roll gets started. How do you recover? We pick up the situation at about 5 degrees right roll, in the range where recovery action has to begin if it's going to be successful. Rightward tail rotor thrust exceeds leftward force due to left cyclic because you've coordinated left pedal with increasing collective. Then main rotor thrust exceeds aircraft weight, so there is not only a right roll moment, but it's a strong force that's tending to roll the aircraft rightward at an accelerating rate as collective increases. Now you need to counteract all these forces simultaneously to stop roll right and settle the aircraft back on the ground. You apply a large left cyclic input to increase leftward force. This shortens the arm along which right roll moment is acting. At the same time, you reduce collective to bring main rotor thrust below aircraft weight, which reduces the power of the right roll moment, while you coordinate that with reduced left pedal, which reduces tail rotor thrust rightward. Now the left roll moment due to aircraft weight works for you over its long arm, overcoming forces up and to the right. If you do all this soon enough, and remember, you've only got fractions of seconds to play with, the aircraft should settle and you can start the takeoff all over again, with better control this time. It should be obvious now that a left crosswind, CG offset to the right, or downslope to the right, are all complicating factors that aggravate the problem by reducing the critical angle at which rollover will take place. Getting back to that collective for a moment, you can't just dump it. You've got to reduce it at a rate that won't cause blade contact with the fuselage. In the UH-1, it's about 40% in 2 seconds. The longer you delay recovery action, the worse off you are. Always reduce collective as prescribed, because that buys you the most in terms of getting the aircraft back under control. You've got weight greater than thrust working for you. Unfortunately, if you let the aircraft get to and beyond the critical angle, even that won't help. Because while you may be able to stop the increase in rate of right roll motion, you'll no longer be able to stop it altogether. And over it goes. Now, we've also said a helicopter can roll over to the left, but now the situation is a little more favorable, and it takes more effort to get yourself into trouble. Let's say we start with the aircraft light on the skids, with tail rotor thrust just equaling left cyclic force. Say you then inadvertently apply strong left cyclic, while failing to coordinate it properly with compensating left pedal action. Leftward force due to left cyclic now exceeds rightward force due to tail rotor thrust, meaning there is net force leftward. This sets up a left roll moment around the left skid, so the aircraft wants to roll to the left. As you now abruptly increase collective and apply left pedal, this roll moment grows in power and is acting over a very long moment arm. The weight of the aircraft is doing less good because its rightward roll moment, which should be a stabilizing force, is acting over an arm that is decreasing in length. The net result is a powerful impulse driving the aircraft to roll left. Assuming no corrective action is taken, let's see what happens. Plainly, more of the same. Due to left cyclic, main rotor blade strike occurs much earlier. Avoiding left rollover gets back to basics. Don't let it get started in the first place. Use correct takeoff procedures. But if you do experience left rollover for whatever reason, recover by reducing collective as prescribed and counter the leftward rolling force by using right cyclic. If you do this the instant you sense rollover starting, you're likely to recover. The critical angle remains the same and is affected by right crosswinds, left CG offset, and downslope left conditions. Everything we've said about dynamic rollovers from level ground applies equally well to rollovers during takeoffs from upslopes both left and right, starting at the point at which the aircraft achieves a level position, and provided there is no translational motion toward the slope. Such motion is a lot like stubbing your toe while walking or running. It complicates the problem of staying upright. Add translation to the right on top of the other forces involved in right rollover, and you've really got problems. Dynamic rollovers can happen during landings too, aggravated if you use rough control action to counter upslope rollover. Get too enthusiastic about it, and you can roll in the other direction the moment the free skid hits the ground. The other obvious complicating factor is that main rotor blade tips don't have as much terrain clearance on the upslope side, so you can get blade strike even before you've used up available cyclic control. This is particularly so in the upslope left situation, when you've already tilted the tip path plane left a few degrees. Critical angle gets severely reduced, and if you get involved in left rollover, you may not have time enough to get yourself out of it. Of course, most pilots really pay close attention when maneuvering around slopes, and that's mainly what's likely to keep you out of trouble. Now, transfer that same degree of attention and concentration to operations on level surfaces, and you've got a lot going for you. That, plus performing every single takeoff you ever make using correct procedures as you learn them in basic. Now, let's look at aircraft characteristics and what effect they might have on dynamic rollover. We've used the UH-1 for explanation purposes, so let's start there. This helicopter typically lifts off nose high, so skid toes rise first, followed by the right skid heel, and then by the left skid heel. During right rollover, the right skid heel may stay in contact, leading to pivoting in yaw about this point along with roll to the right. In left rollover, that skid heel can become the pivot point. The AH-1 Cobra has a relatively high center of gravity, and this is reduced if it is carrying stores. This aircraft lifts off nose down, right skid rising first. Skid toes are forward of the mast, so the likelihood of rollover pivoting may be reduced. In the OH-58, location of vertical center of gravity position is not usually a factor, and this aircraft has a small incidence of rollover accidents, although the two are not necessarily related. This aircraft also rises nose down. Vertical CG location is not considered a factor in the TH-55 either, in the context of dynamic rollovers. This aircraft, which rises nose down, is used extensively for pilot training. This puts the monkey on the instructor's back, of course, because while a student might readily get into rollover out of inexperience, the instructor must be constantly watchful at the instant of every liftoff, ready to take control if rollover seems likely. Knowing the full story about rollover characteristics involves not only knowing yourself and your aircraft, but about environmental factors external to the aircraft that can contribute to rollover problems. Dynamic rollover happens during takeoffs from level prepared surfaces with no local obstructions, as well as unprepared surfaces of all kinds. Although your operator's manual or checklist may not emphasize it, you need to be aware of conditions that can get you into rollover. So let's review a few of them. A level concrete surface doesn't seem to pose many problems, but check the skids out anyway, to be sure a skid isn't in a hole or a crack that could cause problems, especially if the aircraft drifts during takeoff. And look out for projecting expansion joints. Adhesive surfaces like hot asphalt can stick to skids or lower the skid into grooves that can grip the skid long enough during liftoff to initiate rollover. Watch out for grooves, gouges, or other depressions too, as well as bumps or ridges acting as possible obstacles. Perforated steel planking contains lots of steel fasteners that sometimes protrude above the surface. Hang up your skids on one of these, and you're a candidate for rollover for sure. In all these cases, you want to avoid taking off from any surface that might help set up a roll rate, particularly to the right, that could result in rollover. Unprepared surfaces can produce all kinds of problems, including the effects of weather extremes. Snowy surfaces are tricky because skids can break through the surface crust to become entrapped down in the snow. Icy surfaces can be even worse, covered with cracks, pits, bumps, and ridges, all of which can cause trouble. Water frozen beneath or around the skids can trap them in a bond that grips them tightly, making rollover highly possible. Almost any kind of vegetated terrain, level or sloped, includes many possible obstacles around the landing site. Be aware of ditches or other depressions, mounds or clumps of grass or small shrubbery, rocks, branches, or roots from trees. You can spot tree stumps easily. Swampy areas provide uncertain bottom conditions, subsurface obstacles, as well as others visible on the surface, any or all of which can set up conditions for rollover at takeoff. Generally speaking, though, environmental conditions and aircraft characteristics only aggravate the conditions that lead to dynamic rollover in the first place. Let's keep firmly in mind the idea that rollover can and often does take place as aircraft take off from smooth, level, prepared surfaces with no nearby obstacles. This should tell you that the real problem starts with you, that dynamic rollover is almost entirely a procedural problem that only you can do anything about. The more experienced you are, the more it's necessary to get back to basics, to the correct takeoff procedures you learned early in your flight training. You need to discipline yourself to pay close attention to the circumstances at hand, and you need to concentrate intently on what you're doing during the instant of liftoff to hover, because the next few seconds will tell the tale. Successful takeoff or dynamic rollover. Just to refresh our memories of just what the liftoff to hover maneuver really involves, let's watch it one more time. Takeoff check completed. Aircraft cleared. Cyclic and pedals in neutral. Slowly increase collective with a smooth, constant, positive pressure, checking control responses. Apply pedal to maintain constant heading, applying cyclic as necessary to prevent sliding as aircraft gets light on the skids. Maintain smooth application of collective with cyclic coordination to prevent drift, maintaining vertical ascent and heading to hover altitude. It doesn't seem like all that much, but maybe that's part of the problem. Take it for granted, fail to pay attention, concentrate at the critical moment, handle your controls abruptly, and you could be in big trouble, fast. No matter which of the aircraft we've talked about that you fly, dynamic rollover is an ever-present possibility. To help you visualize the problem of dynamic rollover, how to avoid it, and how to recover from it, we first went through the correct procedure for takeoff. With that as a foundation, we showed the forces acting on the aircraft during liftoff. First, during a normal maneuver, then during rollovers both right and left from a level surface. Then we talked about slope operations, indicating that everything is about the same as soon as the aircraft reaches a level position, and we reviewed some of the special considerations involved. Next, we looked at various aircraft types to see what effect, if any, their particular characteristics have on the rollover problem. And we reviewed the problems connected with taking off from various types of surfaces, both prepared and unprepared. We wrapped up with a review of correct takeoff procedures, because that's where rollover avoidance really begins. Dynamic rollover? It's a people problem, and you're the people involved. Follow and practice the takeoff procedures as prescribed in your aircrew training manual, and you'll never roll your aircraft during liftoff. You can count on it.
Loss of tail rotor effectiveness, or as it is commonly called, LTE. What is it, and what causes it?
Can you tell me what loss of tail rotor effectiveness is?
Loss of tail rotor effectiveness is? Loss of tail rotor effectiveness is sort of a misnomer.
Loss of tail rotor effectiveness is an uncontrollable yaw to the right.
Loss of tail rotor effectiveness is a tendency of the aircraft
it's the loss, or it's the inability of the tail rotor to be effective during all phases of flight.
What if this question had been asked of you? Could you have correctly stated what LTE is and what causes it? LTE is defined by the operator's manual as the occurrence of an uncommanded and rapid right yaw, which does not subside of its own accord and which, if not quickly reacted to, can result in loss of aircraft control. Now that LTE has been defined, it is vitally important for all to learn the causes and the proper corrective actions. The Training and Doctrine Command, TRADOC, and the Army Material Command, AMC, Joint Special Study Group investigation of the OH-58 LTE phenomena has identified 3 relative wind regions which adversely affect aircraft controllability. They are weather cocking, vortex ring state, disk vortex. We will look at each region individually. The influence of the weather cocking region will be felt when the relative wind azimuth is 120 degrees through 240 degrees. Besides causing a high pilot workload, tailwinds are a yaw rate accelerator. If the pilot allows the tail of the aircraft to move into this region during a right yaw, the yaw rate can increase very rapidly. When flying in a tailwind condition, the pilot must, by smooth application of pedals, not allow a yaw rate to build. The pilot must remember that a tailwind can rapidly accelerate a pilot-induced right turn. A tail rotor vortex ring will form with a relative wind azimuth of 210 through 330 degrees. To counter the main rotor torque, the tail rotor produces thrust to the right. As a result, the tail rotor wash is to the left. A left crosswind opposes this wash. These wind tunnel segments will show the effects of a left crosswind. The model is positioned in the wind tunnel at the heading for a relative wind azimuth of 270 degrees, and the tail rotor is operating at a constant pedal setting. Smoke is used as an airflow visualization device. This sequence shows the tail rotor operating in the normal working state with a crosswind of approximately 5 to 10 knots. The tail rotor is just entering the area of unsteady airflow. Pilot workload in this area will begin to increase as he attempts to compensate for the aerodynamic oscillations. As the wind velocity is increased, the unsteady airflow also increases. With an approximate wind velocity of 10 to 20 knots, the tail rotor vortex rings become visible. Observe that a ring will form and build in size. As the ring increases in size, its strength will weaken, allowing the left crosswind to blow it away from the tail rotor. This dissipating action is evident by diffusion of smoke. It is the formation and shedding of these vortex rings which cause the tail rotor thrust oscillations to occur. Notice that the rings form and dissipate very rapidly and at random intervals. It is this mechanism that produces the high pilot workload associated with flying in this region. Observe the motion of the tail rotor and vertical fin. The model is rigidly mounted, thus the tail boom is shaking. In an actual aircraft, the pilot would see this as a rapid left and right yaw moment. As the left crosswind velocity increases from approximately 20 to 35 knots, the tail rotor moves into the windmill brake state. Notice that as the wind speed increases, the vortex rings will become less apparent and will eventually disappear altogether. Pilot workload in this area will begin to decrease as the left crosswind velocity increases and the airflow through the tail rotor once again becomes smooth. The pilot's major concern in this area would be the weather vaning capabilities of this crosswind. The wind is strong enough to force the aircraft into a left yaw, which the pilot must correct with right pedal. If the application of right pedal causes the aircraft to yaw right to where the relative wind moves into the weather cocking region, the yaw can rapidly progress into a spin. The final region to look at is disk vortex. This becomes a factor with a relative wind azimuth of 280 through 330 degrees, and when the velocity is between 10 and 30 knots. Vortices are generated as a function of lift. The greater the lift, the stronger the vortex. This segment shows the strength and size of the vortices created by a heavy jet. A rotary wing aircraft also generates vortices, and these vortices move with the relative wind. The size and intensity of the main rotor tip vortices can be seen here as they trail downwind. Notice that the vortices are sharply defined. This wind tunnel sequence shows the top view of the OH-58 main rotor disc vortex. The smoke is placed on the edge of the main rotor disc. Notice again that the edge of the vortex is well defined. The model is now positioned with a relative wind azimuth of 330 degrees. An actual aircraft at this point would have a tendency to yaw left into the relative wind. To maintain a constant heading in this position, a pilot would be applying a slight amount of right pedal pressure. The model is now positioned with a relative wind azimuth of 320 degrees, just 10 degrees difference from the previous position. The diffusion of smoke indicates the tail rotor is now operating within the influence of the main rotor disc vortex. It is at this point that a sudden tail rotor thrust reduction will occur. The thrust reduction occurs because of the airflow changes experienced at the tail rotor as the main rotor vortex moves across the tail rotor disc. The pilot must be prepared to apply additional left pedal to prevent the aircraft from yawing right. This sequence shows a side view of the main rotor disc vortex when viewed from the left. It clearly shows the main rotor vortex as it is blown rearward by the wind. As the model is yawed to the right, notice how the main rotor vortex intersects the tail rotor disc. Again, it is this vortex and its turbulence which causes the sudden decrease in tail rotor thrust. It is important to note that there are two areas of overlap. Control of the right yaw rate is critical when flying in either of these areas. The pilot must be aware that left pedal application is critical to prevent a right yaw from progressing into a spin. Now that you have seen what causes a loss of tail rotor effectiveness, the next obvious question is, what can I, as the pilot, do to avoid an LTE situation? Therein lies a problem. As a scout pilot in the terrain flight mode, you cannot avoid an LTE conducive environment. As you maneuver about the battlefield, you will be subjected to continuously changing wind directions and velocities. So, how can you reduce the likelihood of encountering LTE? There are 5 important points for you to remember to help avoid an LTE situation. The first 4 are specific points that are culminated in the 5th point. They are: 1. Develop a feel for the aircraft and how it will react under varying wind conditions. 2. Develop the ability to read the winds. By observing trees, smoke, grass, and other objects, you can estimate the direction and velocity of the wind. 3. When possible, make left turns. When making a left turn, the pilot will, in effect, be increasing the tail rotor thrust and therefore be more sensitive to the need for left pedal input. 4. Avoid excessive movement of the flight controls. Over-controlling increases the likelihood of getting behind the aircraft. By smoothly coordinating control inputs, the odds of encountering an LTE situation can be reduced. 5. Fly the aircraft. This is really a summation of the above 4 points. Terrain flight is very demanding and requires the pilot to give the flying of the aircraft his full attention. You must be sensitive to what the aircraft is doing. You might be thinking, I always fly the aircraft. What a dumb statement. If this is running through your mind, then let me ask you. As you could see from these scenes, you think you are flying the aircraft, but in reality, are you? In all situations, the pilot's first priority is to fly the aircraft. If you find yourself in an accelerating, uncommanded right yaw, it is critical that you simultaneously apply left pedal and forward cyclic. The use of the collective will be at the pilot's discretion based on altitude. This sounds simple, but remember, this procedure must be done instantly. Other factors which may be present can significantly influence the severity of the onset of LTE. These factors include gross weight, density altitude, low indicated airspeed, power droop. You cannot, as a scout pilot, avoid the environment that could lead to an LTE occurrence, but you can, by understanding what causes it, avoid the situation in most cases. You must, above all, remember to always fly the aircraft. Based on test results from various organizations, the U.S. Army Safety Center feels the main rotor disc vortex effect is the most significant influence in entering LTE. Additionally, this region produces the most rapid and violent onset of LTE. As a result of numerous accounts of LTE, the U.S. Army Aviation Systems Command, AVSCOM, has developed product improvements for the OH-58A and C helicopters. When applied over the next few years, these PIP should significantly reduce the incidence of LTE. In a March 1984 message, the Vice Chief of Staff of the Army directed, in order to prevent loss of tail rotor effectiveness accidents with the OH-58s, which have not had the power droop and improved tail rotor product improvements installed, the following restriction is imposed. OH-58s without the above PIPs will maintain a minimum of 35 knots indicated airspeed in forward flight, regardless of altitude. The exceptions are A, approved OH-58 terrain flight training and operations, B, landing, takeoff, and hover in ground effect, C, maintenance test flights, D, life-threatening situations, actual emergencies, and E, special missions when approved by Aviation Commander 05 or higher on a case-by-case basis.
All aircraft are designed for specific weight limitations and balance conditions. An overloaded aircraft may cause structural failure or result in reduced engine and airframe life. An unbalanced aircraft may create longitudinal fore and aft instability. Since both weight and balance have a direct bearing on performance and control, a pilot should never fly until he is completely satisfied with his aircraft's loading. If he does, he is only inviting disaster. Now, to calculate the balance status of an aircraft, you must first have a working knowledge of the principle of moment. During this program, you will learn how to compute moment, the effects of moment on an aircraft, and how moments are used to calculate an aircraft's center of gravity, or CG. Now, what does the phrase principle of moment mean? A moment is the product of a force or weight in an aircraft times a distance. The distance used in calculating a moment is called the arm, and is usually expressed in inches, and is measured from a desired known point on the aircraft referred to as the reference datum line, or RDL. In order for an aircraft to be in balance, the sum of the moments on each side of the balance point, or RDL, must be equal, which is the principle of moments. To demonstrate this, compare the profile of this helicopter to a lever which has been placed on a fulcrum. The pivotal point equal amounts of the lever on either side. The numbers will designate the distance out from the pivotal point in inches. The reference datum line, or RDL, is placed over the pivotal point. As you recall, the RDL is the line from which you make all measurements for weight and balance purposes. With this lever, you have two possibilities of rotation. The first is clockwise rotation, indicated as a plus or positive value. The other, of course, is counterclockwise rotation, which is designated as a minus or negative value. These signs are used to differentiate between the turning motion of the two sides. You can see that this lever is in balance because you have equal amounts on each side of the RDL. So with the aircraft, of course, you are mainly interested in balancing it about a certain point. Now, to demonstrate this, we'll take 100 pounds of weight and place it on the clockwise side, 5 inches out from the RDL. Realizing, of course, with this weight on the clockwise side and none on the opposing side, the lever will rotate in a clockwise direction. In weight and balance, you must have a means of determining the measure of the rotating force created by any weight. You can do this by using the moment formula. Weight times arm equals moment. To determine the turning effect produced by this weight, 100 pounds, at this distance, 5 inches, substitute the values into the formula and multiply them out to get the moment. A 100-pound weight times a 5-inch arm produces 500 inch-pounds of moment. Thus, the turning effect is 500 inch-pounds in a positive direction. Now, to balance out the lever, the easiest way would be to put the same amount of weight, 100 pounds, at the same distance out on the opposite side. So, by using the formula again and substituting the values, a 100-pound weight times 5 inches out, you come up with 500 inch-pounds of moment, proving out mathematically that this lever is now in balance. The law of moment states that for a state of equilibrium, the sum of the total clockwise moments must be exactly equal to the sum of the total counterclockwise moments. With an aircraft, however, you do not always have the same amounts of weight to place, nor do you always have the same distances available to place the weights. Yet you must come up with a balanced condition. So let's use the lever again and show how you can have different weights at different distances and still come up with a balanced condition. Let's remove this 100-pound weight from the counterclockwise side and replace it with a 125-pound weight. Now you need to figure out where to place this 125-pound weight to balance the lever. First, you have a couple of known factors. You have the weight, 125 pounds. However, you do not know the distance out to place it. But you do know that you must create 500 inch-pounds of moment as indicated on the clockwise side, equal amounts of moment on both sides. With your two known factors, you can figure the unknown. It is a matter of dividing the known factor, weight, into the known moment required, inch-pounds, and this will give you the number of inches out to place the weight. So 125 into 500 would produce an arm of 4 inches. Substituting the arm of 4 inches into the formula, 125 pounds times the 4 inches gives you the required 500 inch-pounds. Therefore, if you place the 125-pound weight at 4 inches out on the counterclockwise side, you will then have a balanced lever. Consequently, you can have unequal distances and unequal weights and still be able to come up with a balanced condition. With this type of lever, you have been concerned with positive and negative moments. Dealing with negative and positive values in a mathematical computations creates more room for error. When you use these same principles to determine an aircraft's center of gravity, this room for error has been eliminated. This is due to the placement of the RDL, which is usually located at or near the nose of the aircraft, to eliminate arms with a negative value. Earlier, You are working about a given pivotal point to balance a lever. But with an aircraft, you want to determine where the center of gravity is after it is loaded, and if it falls within the center of gravity limits. When this has been determined, your aircraft is then perfectly balanced for flight. To demonstrate this principle, let's use a board 20 inches in length. Now, the first thing we must do is to establish an RDL. For this demonstration, the RDL will be located to the extreme left. You can see how the minus distances and minus moments have been eliminated. All dimensions and moments now become positive. Now, let's say this board is lying on the floor, and we'll put some weights on it, determine its center of gravity, and then support it at that point on a fulcrum. First, we'll place a weight 20 pounds, 12 inches from the RDL. Next, a 10-pound weight 9 inches out. And lastly, a 15-pound weight 5 inches out. Now, you have 3 weights applied to the board. No matter how many weights you might have involved, the principles are still the same. Next, determine the moment created by each individual weight. With weight and balance, you cannot sum up a series of arms and weights and multiply them out and get the same result. It will not give you the correct answer. Instead, each item must be handled individually. So, using the moment formula again, weight times arm equals moment, substitute your values and multiply them out. The 20-pound weight times the 12-inch arm produces 240 inch-pounds of moment. The 10-pound weight times the 9-inch arm produces 90 inch-pounds of moment. And the 15-pound weight times the 5-inch arm produces 75 inch-pounds of moment. Now you will have to add up the weights and moments and apply them to another formula. When you sum up the 2 columns, you come up with 405 inch-pounds of moment and 45 pounds of weight. With the total weights and total moments, you can insert these values into the center of gravity formula to find the center of gravity. Center of gravity is the total moments divided by the total weight. Substituting your known factors into the formula, 405 inch-pounds divided by 45 pounds will give you a center of gravity of 9 inches. 45 into 405 goes 9 times. Your pounds of weight into pounds of moment cancel out, leaving you with inches. So your center of gravity is 9 inches from the same reference point from which all your measurements are made. Remember, in any weight and balance problem, you must use the RDL in the same position, and all measurements, including the final center of gravity, are measured from that point. Should you pick up this board and place it upon a fulcrum 9 inches from the RDL, the board would balance. This is the balance point, your center of gravity. This principle applies exactly the same to an aircraft. Using the outline of an aircraft, let's place some cargo aboard it, determine the moments created by the cargo, and then determine if the aircraft's center of gravity is proper. You must first establish a reference datum line. This information, which has already been determined by the manufacturer during the design of the aircraft, can be found in the aircraft's operator's manual. All measurements have been made from this point, so for weight and balance purposes, you must make all measurements from this point. As mentioned earlier, the RDL is usually located near the nose of the aircraft. For aircraft loading, the distances from the RDL are referred to as stations. For demonstration purposes, let's use a U-860 Blackhawk and place a 50-pound weight at station 285, a 120-pound weight at station 315, and finally at station 365, a weight of 60 pounds. Now it is just a matter of finding the moment created by each of these 3 weights. First, you have the 50-pound weight at station 285, producing 14,250 inch-pounds of moment. Then you have the 120-pound weight at station 315, creating 37,800 inch-pounds of moment, and the 60-pound weight at station 365, producing 21,900 inch-pounds of moment. Now that you have the weights and moments of the cargo, it is necessary to add these values to the basic weight and basic moment of the aircraft, which is established on Chart C, DD Form 365-3, by any given aircraft. These are the base figures from which you work. So the basic weight of this aircraft is 13,692 pounds, and the basic moment is 4,987,000 inch-pounds. Below these two values, you see the weights of the three pieces of cargo and the moments created. Summing up these two columns of weight and moment, you find that you have a total weight of 13,922 pounds and a total moment of 5,060,950 inch-pounds. With these values, total weight and total moment, simply insert them into the CG formula to determine the CG. Total moments divided by total weight equals center of gravity. Substituting in the formula that 5,060,950 inch-pounds of moment divided by 13,922 pounds of weight will produce a CG of 363.5 inches, which is now the aircraft's center of gravity after it has been loaded. Now you will need to check the CG limits of the aircraft specified in the aircraft's operator's manual to see if your center of gravity falls within the limits. For this particular aircraft in weight, the U-860, the CG limits are stated as 343.2 inches forward and 366.0 inches aft of the RDL. You determined your CG as being at station 363.5, which, as you can see, falls well within the 343.2 and 366.0. This aircraft is now safely loaded and balanced for flight. This program has briefly explained the procedures involved in determining weight and balance of an aircraft. With a better understanding of the principles of moment, you should be able to properly load your aircraft within the proper weight limit and balance range and feel confident and safe in the performance of your